Today's lesson is talking about continuity. We're looking at sections 1.5 through 1.6. To get started, I've written up a definition of what it means for a function to be continuous at a point. And if you read it, it says that there are three things that need to be satisfied. So if you're asked whether or not a function f is continuous at a given point, all three of these things must be shown. It is not okay to just show three. You must show 1, 2, and 3. 1 being that the function exists at the point, 2 being that the limit of the function at the point exists, and 3 finally being that the limit is equal to the value of the function. So for our first example, we're asked about two functions, whether or not they're continuous. And if they're not continuous, where are their points of discontinuity? So problem A is a rational function, and from Algebra 2 and pre-calculus, you probably already know that typically rational functions have asymptotes, and if they don't have asymptotes, then they have holes where something's canceled out. Okay? So it's safe to assume that this function is not continuous, and its point of discontinuity is because that's what makes the denominator 0. B looks a little more complicated, but it's really sort of the same idea that's going on in A. In B, we have a rational function that's defined everywhere except 4. That's where the hole happens to be. And then we fill that hole with 3. So if this function were simply the top piece of this piecewise function, then it would be safe to say that this function is not continuous because it has a discontinuity at 4. However, if we simplify this top part by factoring, you see these two factors cancel out, and we could rewrite f as x plus 2, where x is not equal to 4, and 3 when x is equal to 4. So this top part is simply a line However, at 4, there's a hole. Now the question is, does this fill that hole? So at x equals 4, I'm at 3. And it's plain to see that that point does not fill the hole. Therefore, the function is not continuous. And its point of discontinuity is in fact at 4. So before we move on, I think it's important to note that there are two functions, polynomials and rational functions, that have sort of stated facts about their continuity. Every polynomial is continuous everywhere. And a rational function is continuous at every point where the denominator is non-zero. And it has discontinuities at the points where the denominator is equal to 0, as you just saw in the previous two examples. This next theorem, abbreviated as IVT, stands for Intermediate Value Theorem. It is going to be a fairly important theorem in this chapter and later on down the road. It's a fairly straightforward theorem, but it's important that we start learning how to use theorems to our advantage so that on the AP test, you don't make a mistake by not proving one of the hypotheses before you state a conclusion and lose points. So what I'm going to do is highlight for you the two hypotheses of the intermediate value theorem, and then I have a small diagram to demonstrate graphically what the intermediate value theorem guarantees. And next, we'll do an example using the intermediate value theorem. So the intermediate value theorem has two hypotheses. The first is that f must be continuous. Okay? And it must be continuous on a closed interval, AB. The second hypothesis of the theorem is that k is a number between f of a and f of b. All right? So I have 1, 2 hypotheses that must be shown before I can conclude that there must exist at least one point x that is between a and b and f of x is equal to k. So that last part, my conclusion, I'll show over here. If I have a continuous function, which this is, we'll say it's a polynomial, therefore it's continuous everywhere, and f of a and f of b bound k, in other words, k is a number between f of a and f of b, then it must be the case that there is some x value that is between a and b that will take me to that k value. That k value is my intermediate value. So next, we'll look at an example using the intermediate value theorem, hopefully make it a little bit easier to understand what I mean by two hypotheses and a conclusion. So in this example, we're asked to actually use the intermediate value theorem to prove that a zero exists for a given function on some interval. Now remember, I said that there were two hypotheses that first needed to be stated in order to make the conclusion that the intermediate value theorem guarantees. That first hypothesis was that the function was continuous. Well, f is a polynomial, so therefore it is continuous. The second hypothesis was that the point I was interested in along the range was between the endpoints of the range of my interval. So f of 0 is -1 and f of 2 is 5. Well, for a function to have a 0, it means that at some point the function actually equals 0. Well, 0 is between -1 and 5. So we'll let k equal 0, and f of 0 is less than k is less than f of 2. So the point I'm interested in, k, is between the range of my interval. The two hypotheses lead to the conclusion that, therefore, there must exist at least one x on the interval 0 to 2 such that f of x is equal to k, which we said was 0. So intermediate value theorem used to prove that a function has a 0 or has a solution if this is equal to 0. The last theorem we're going to talk about today is the squeeze theorem. You may or may not have heard of it from pre-calculus, but if you haven't, we're going to talk about it today. Instead of writing out the full theorem that's in your textbook, I went ahead and just drew a picture and a short description of what the theorem is talking about. The theorem's rather lengthy and it would take a long time to write out on the board. So the squeeze theorem pretty much involves three functions: f, g, and h. They don't have to be named f, g, and h. Those are just the three functions I decided to use. Now it has to be the case that on some open interval a to b, this must happen. H of x must be less than g of x must be less than f of x. And there is some point c between a and b. So notice over here, outside of a and b, this statement is not true. But that's okay as long as there is some interval surrounding c that this is true. And it is true on this interval. Okay? If we have the limit of h of x as x approaches c equaling L, and the limit of f of x as x approaches c equaling L, if g of x is in the middle, it must be the case then that, therefore, the limit as x approaches c of g of x must also equal L. And you'll see in the last example today that we do where this can come in very handy when trying to approximate the limit of a function that is rather difficult to comprehend. So in this final example for today, we're going to look at two rather curious functions. You may have seen the function sine of 1 over x, and maybe even have graphed it. But have you ever wondered whether or not that function approaches a limit as x approaches 0? If you've never graphed that function, go ahead and graph it yourself. And I'll show you what the graph sort of looks like up here. When you graph it, it might look something like that. And there's a bunch of little oscillations going on in here. We want to know what's going on. So we take the limit as x approaches 0 to find out what's going on. Well, if we think about this, as x approaches 0 from the positive direction, this approaches infinity. And as you know, sine, as it approaches infinity, if we're thinking about 1 over x as the input for the sine function, as sine goes off to infinity, it oscillates between 1 and negative 1. So in here, very close to 0, coming from this direction, we're oscillating between negative 1 and 1. Similarly, as x approaches 0 from the negative side of 1 over x, we approach negative infinity. And as sine goes in the negative direction, we again oscillate between 1 and negative 1. So this limit does not exist because at 0, or as we approach 0, we oscillate without any dampering in amplitude. Now let's look at the limit of x sine of 1 over x. And if you've gotten ahead of me and you've graphed it, maybe you can guess at what the limit is going to be, but we're going to prove to ourselves that that limit does exist. Well, we've already said that the function sine of 1 over x is always between 1 and negative 1. Well, if that's the case, multiplying through by absolute value of x that must also be true. And if you think to yourself, all that x does outside of a trig function is adjust the amplitude. So if I were to say that the amplitude of this sine function is now 2, then yes, in fact, this will be between 2 and negative 2. Okay. Well, we know what these two functions look like. One looks like this. And the other looks like this. And if you graphed x sine of 1 over x, you might see a graph that looks something like this. Well, what's the limit of these two bounding functions? Let me write this here. Well, if the limit of these two bounding functions both equals 0, and we could limit ourselves to some interval, say 2 or pi, negative pi to pi, and x sine of x is always between those two functions, then the limit of x sine x of 1 over x as x approaches 0 must be 0. And that is an example of using the squeeze theorem to prove that a limit exists. Well, that's all for today. Thanks for watching. See you next time.